In the next few lectures, I'm going to discuss colligative properties of solutions, as well as a little bit finer detail on what a solution is. So first, I'd like to mention the difference between suspensions, colloids, and solutions. And these are three different mixtures that we meet or we find in the lab and in our lives. So we've talked a lot about defining solutions. They're homogeneous mixtures, and so that means they're uniform. And that's really key to what a solution is. It's this perfectly even distribution of the two things you're combining, or three. So these cannot be separated unless you evaporate off one of your liquids compared to the other. But there's not a filter paper that can separate a solution. Now, a suspension is something that is a heterogeneous mixture. So these are non-uniform. The trick with suspensions is that they look like solutions. It looks all the same. But usually, if you set it down on the table and you leave it alone for a long time or a short time, the particles settle down. So this is the kind of like a snow globe. The suspension is particles that are very, very small, and they're just suspended all over the place. And if you give it time, they settle all down to the bottom, and then you have clear solution above it. And so this means that they can be filtered. And so you can separate the particles. They're large enough that a filter paper will separate them from the water or the other liquid. And in between these two is this kind of gray area, middle ground, and that is colloids. Now, they are heterogeneous mixtures just like our suspensions. But they are much smaller particles than our suspensions. They're super tiny. And so they can't be filtered, so this won't work. But they can still be separated. It just requires a semi-permeable membrane, which only allows certain things through of a certain size. And so the separation step for colloids is really extreme. Some examples of colloids include shaving cream, which you can imagine would be a real treat to try to put through filter paper, or things like mayonnaise. Things that if you let them settle, they won't separate on their own. Though I think I might be terrified if I ran into mayonnaise that had separated. And then my favorite colloid, of course, would be ice cream. Ice cream doesn't change if you let it sit out on the counter other than melt. But what it is it's a colloid of fat particles and air bubbles and ice crystals and more flat globules. And they're all very, very small particles that you would be able to separate with a semi-permeable membrane. And so it's not actually a solution, even though to our eyes, it looks like a perfectly homogeneous mixture if you're looking at something that is flavor without any additional add-ons. Like mint chocolate chip is not a solution or a colloid. It's very, but that's looking at the chocolate chunks in it. And so some of the things that we might classify as a solution we should be careful about, because they might actually be a colloid. And those particles that are mixed together are bigger than individual molecules, but smaller than something that would fit through filter paper. And so when we talk about colligative properties, we're only talking about colligative properties of solutions. This only applies to our solutions. It doesn't affect colloids, and it doesn't affect suspensions. And these are properties that are magical in that they depend only on the concentration of the solute and not its identity. So it doesn't matter if my solution is sodium chloride as a solute or sugar. The only thing that matters is my number of actual molecules, or we'll actually call it the number of particles that are suspended in the solvent. So that number becomes really important, and we'll see that this is going to depend on if something is a strong electrolyte or non-electrolyte too. So examples of colligative properties are the elevation of boiling point. So as you have more particles in solution or a higher concentration of solute, the boiling point of the solution will increase. So as concentration of solute increases, the boiling point increases. And this is the boiling point compared to the pure solvent. We then also see a lowering of the melting point. So our melting point will decrease with concentration solution. And we see a pressure that we associate with osmosis, so osmotic pressure. So in this video, I'll address boiling point elevation and melting point depression, and then we'll focus most of our time in the next lecture to osmosis. So boiling point elevation first. Here we go. Boiling point elevation will, and this is just looking at water, so it depends on the type of solvent that you're looking at. It'll have different changes in the boiling point based on the amount of the solute. But for water, which is I think our most common solvent, if you have a kilogram of water, you will increase that boiling point 0.51 degrees Celsius if you add 1 mole of solute. So if I have 1 mole of, let's say, methanol, write out the chemical formula, which is a non-electrolyte, in 1 kilogram of water, my boiling point would increase from 100 degrees Celsius to 100.51 degrees Celsius. Now, if I had 1 mole of sodium chloride and 1 kilogram of water, this wouldn't exactly be the same because it's the solute particles. So my sodium chloride in water becomes Na plus and Cl minus. So I'll have 1 mole of my sodium cations and 1 mole of my chloride anions. So I'll really have 2 moles of particles in 1 kilogram of water. So my boiling point would be, up here, we go from 100 to 101.02. So a bit more of an increase. Now looking at freezing point depression, it doesn't mirror this exactly. So we actually see a larger change in the freezing point based on the amount of solute added. So again, we're just looking at 1 kilogram of water, and to decrease the freezing point by 1.86 degrees, you need to add 1 mole of a non-volatile solute. So if I added 0.5 moles of sodium chloride, which breaks up into Na plus and Cl minus, I'll have 0.5 moles of cations plus 0.5 moles of my anions to give me 1 mole of particles. I'll have a freezing point of water that goes from 0 degrees Celsius to negative 1.86 degrees Celsius. So if it is freezing cold out and you salt your driveway, you're salting your driveway because it lowers the freezing point to have solute around. And usually you're going for more than a mole. Like people really salt the roads, a lot of it, and so it helps melt any ice and prevent it from forming. So let's do this example. If you'd like to pause the video and try it on your own first, I'd encourage you to do so. All right, so in this one, we're looking at what is the freezing point of 1 kilogram of a solution that's 5 molar and has sodium hydroxide in it, in water. So what we need to figure out here is the number of moles of solute particles. When we assume the density of water is 1, it means that if we have 1 kilogram, we have 1 liter. So if I have a 5 moles per liter solution, and I have 1 kilogram of it, I really have 1 liter. So that means I'll have 5 moles of my solute, which is NaOH. Sodium hydroxide is a strong electrolyte. Sodium hydroxide that's aqueous forms sodium cations and hydroxide anions. This is one of our polyatomic ions. So I'll have 2 particles for every 1 sodium hydroxide. So really, that 5 moles of NaOH becomes 10 moles particles. And I'm looking at freezing point, so I know that for every kilogram, if I have 1 mole of solute particles, I'll decrease my temperature by 1.86 degrees Celsius. And I'm going to have 10. So if I multiply that by the number of moles of particles I have, I'm going to end up with 18.6 degrees Celsius freezing point depression. So that means I'll go from a 0 degrees Celsius frozen water to water that doesn't freeze until it's at minus 18.6 degrees Celsius.